you so much for coming. I'm Julia from the library. It's great to have a full room. I will just remind everyone that the library closes at 8 on the dot. So after this is done, if we could kind of skedaddle, that would be super helpful. Thank you. And yeah, I'm really happy to be having this program since it got canceled because of a hurricane last time we tried to have it. So, and now I'll hand it over to Molly Mulhern from Camden Can to introduce our speaker.
Great, thank you. Thank you, Julia, and thank you all for coming. My name is Molly Mulhern. I'm a Camden resident. I'm here on behalf of Camden Can, which is a grassroots organization that we began about a year ago to bring people in Camden together to talk about climate. And we've had a full year of lectures. This is part of the Camden Talks Climate series. I want to thank Julia for hosting us. We could not do this work without Julia, the librarians of the world, and all of you. So thank you very much. I also want to thank the steering committee. There are a few of them. They could just raise their hand a little bit in the room. Beatty and Sarah, amongst others, some of the others. But the inspiration for these talks comes from every single one of you who inspires us to take seriously what's happening with the changing climate and the wider world. We have a couple of things just to announce to you. In the back, there is a sign-up sheet for a bi-weekly newsletter that Camden Can puts out. It's related strictly to Camden and events that are going on, or either committees or other events that might be of interest. And we try to be respectful of your time. So if you want to sign up for that, it's in the back. We have over 400 readers on that list. So, and we like to keep it growing. Upcoming events from Camden Can in 2 weeks' time, October 15th, it's a Tuesday night in this room. You can see a poster in the back. We'll start the Camden Harbor Resilience Planning, which is a process that hopefully involves every single one of you who live in Camden and want to talk and give feedback to a group of consultants who are helping us envision what Camden should, steps we should take for the next 30, 50, or 100 years as climate forces changes to our harbor. So that's October 15th. It's in this room, 6:30. It will be videotaped. It's Peter Slavinsky, who is the Maine State geologist, will be speaking, but he's also going to be with the consulting group of Richardson Associate and a fellow by the name of Blake Sanborn and his associate Todd Richardson. So that's in 2 weeks' time. We have not yet disclosed this, but we believe in November we'll be doing another talk in here, or actually just a idea gathering session for people to talk about what's next for Camden climate action. So that would be November 14th in this room, we hope. And with no further ado, I would like to welcome Dr. Kerry Emanuel to the stage here. He is apparently familiar with our town from a young age. We were canceled in April due to a blizzard that I'm sure that Kerry could see coming, but he was helpful and was able to reschedule for us. We're very excited based on some of what we've seen in our January storms, but also, of course, what happened over this weekend and the devastation of stronger storms that hopefully he can help us understand and maybe give us some ideas for how to move forward. He is an emeritus professor of atmospheric science from MIT. He's also the author of a much acclaimed book that I fell in love with. It's called Divine Wind, and I would encourage you all to have a look at it. It's a beautiful, intelligent book about what's been happening. So I'm looking forward to hearing what Dr. Emanuel has to say. He's been doing this for over 50 years, and I'm sure he's got a lot to help us understand. So with no further ado, Dr. Emanuel.
Thank you very much, Julie and Molly. And about the cancellation of the blizzard, I should have warned you. My motto is never invite a meteorologist to a picnic. Always something happens on those things. But I'm happy to be with you here tonight. It's nice to see some old friends and familiar faces, and of course the new ones. And unfortunately, it occurs in the midst of a hurricane tragedy, which you're all aware of, down to our south. And I'm afraid that it's turning out to be much worse even than we feared at the beginning. So I won't have very much to say about that, but I'm sure the whole situation will be in our thoughts. So tonight, what I'd like to do is begin just by talking about the history of hurricanes on the coast of Maine. You know, we really haven't had a real hurricane, what we meteorologists call a hurricane, in a long time. We've been kind of lucky that way. And I want to give you a feeling for whether that luck is likely to hold out or not. Talk about the whole nature of natural hazard risk. How do we actually go about treating this as a problem and assessing and managing risk, which is what it's all about on the human side. And then an endeavor which I have devoted a lot of the latter part of my career to is to try to bring the field of physics to bear on assessing risk. The people, scientists who do risk assessment largely for businesses, and scientists who understand the physics of hurricanes are completely separate groups that never talk to one another. That's about to change quickly because we can't assess risk the way we used to. We have to do something quite new in this field. And then finally, I'll talk about applying that to the fascinating and somewhat disturbing problem of assessing how hurricane risk is likely to change because the climate's changing. So I want to preface my remarks, I feel I should, up here in Maine for the two storms that I'm sure many of you experienced last January, 10th and 13th, 2024. And thanks to Joseph Sinkowitz for providing this beautiful pair of satellite pictures. But I want to point out, these are the two storms, right? 3 days apart. They look very similar in many ways. And it was kind of an unfortunate 1-2 punch. The big problem with it is this enormous fetch of southerly winds blowing water right into places like Penobscot Bay. That was the big problem, as you know, was water. It was quite windy here as well, but the water, what you may not know is that in the average hurricane, water is a much bigger problem than wind, and yet journalists and other people always focus on the wind. Well, sometimes we have to be aware of the wind, but the water doesn't get enough attention. Here is, again, thank you to Joseph for this chart, is a record of wind at Matinicus Rock, which is way out there in the entrance to Penobscot Bay. And it's been aligned, these two curves, the orange is for January 10th, the blue is for the 13th storm, but they're aligned for the time of high tide, which is that red bar there. This is sort of the lower axis there is in hours, all right? So this is spanning a bunch of days. And the solid lines are the sort of 10-minute sustained wind that is often reported as the wind speed, and the dots are the gusts. So you see that in the first storm, we had gusts out there well over hurricane force. And those winds, what you don't see in a point chart like this, is extended over an amazing fetch of several thousand kilometers to the south. So the wind was blowing over a big patch of water, and that's what caused so many problems. And it arrived nearly at high tide, and it was unusually high astronomical tide. So those combined to give us what we saw. The upper one's a picture familiar to you of Camden. There's the yacht club in the upper left corner. I live in New Harbor now with my wife, and that's a picture of that I took during the January 10th storm of a neighbor's house, boathouse being flooded. So it was a really catastrophic event for the coast. About $70 million is the estimated damage in Maine from these two storms. The only benefit I can think of from these two is we didn't have to file our taxes this last year until August or July. This is the Rockland Breakwater, and if I can get this to go, let's see.
Just click,
It's a webcam, and I happen to just take a movie of it on my. That you're looking toward the north, and you can see where the breakwater should be. It's completely underwater. Waves are breaking over it. I'll do it one more time. It's quite a spectacular event from the point of view where you certainly wouldn't have wanted to be out at sea at that time. So there we go. Yeah, so the spray from the waves is going way, way up into the air. This is a little bit hard to read. I apologize for that. This is just water levels at Rockland. This is not really very accurate, although there's been a little information. We have actual gauges in Bar Harbor in Portland, And it's not a really good idea to average those two to get water levels in Rockland. But what else are you going to do? I mean, we need more measurements up here for sure. We need more, federal government runs this whole array of surge gauges. And so there's been a little bit of information added on the right. But what I want to point out to you, if you look at the last or second to last column, one or the other, the red events, the red colored lines are all events since 2018. And you can see a lot of the big ones have been since then. All right. So we've had, maybe this is a statistical fluke. There are not enough numbers here to say there's a trend, but we've had a really hard time the last 6 years up here. And this is just another way of doing it. And again, the colored lines are since 2018. And this is sorted by the maximum surge. And in this case, the yellow lines are hurricanes. So what we had in the winter was definitely not a hurricane. I'll try to tell you what the distinction is. Hurricane force winds, yeah, but not a hurricane. Hurricane is called a hurricane because of the way it gets its energy. It gets its energy from the evaporation of seawater, whereas the winter storms like we had in January derive their energy from a temperature gradient on a grand scale in the atmosphere. Winter storms are very common, but of course, uncommonly, you can have very, very intense ones, which was our problem last winter. Two very different kinds of energy sources, but there are hybrid storms that use both. Hurricane Sandy in 2012, which kind of demolished lower Manhattan, was a hybrid storm. All right, so there's a lot to pack into this science, and I'm only going to be able to touch the tip of the iceberg tonight. So we haven't really had an honest goodness hurricane in Maine for a while. And I want to disabuse you of any idea that we somehow don't get them up here, just by talking about some of the ones that we have had in history, almost all of them before even, any of us were around to see them. There might be a few people who are old enough to remember some in the 50s, I don't know. And I would say, yes, you should be worried. We see all around the world a tendency for places which just by statistical fluke haven't had natural catastrophes, whether they be earthquakes or storms, and they lose their resilience to it. And why bother to keep up a storm barrier or any other kind of defense? Why spend tax money when you haven't had one in a while? It's just a natural human reaction. We're kind of in that stage in New England where we've forgotten the history and we're letting things down. Now, that's not going to be a problem here for a while because we got slammed so badly in January. Hurricanes are far rarer up here than winter storms. In Florida, you almost never get winter storms, and hurricanes are more common. Here it's flipped. They can be more violent than the storms we experienced last winter when they occur. So the insurance companies will tell you they're much more worried about the odd hurricane than they are about the relatively common winter storms. We had quite a few, as you'll see in the 1950s and 60s, but only one sort of semi-serious one called Bob since 1972. Bob occurred in 1991, I think. So here are some infamous ones. I should say before I go into this, a couple of things that the last really big hurricane we had in New England, although it didn't affect Maine that badly, was the Great New England Hurricane of 1938. And that was a terrifically violent storm that was moving at a forward speed of about 60 miles per hour when it struck Long Island and caused seismic waves that were recorded all around the world, the landfall of that hurricane. Here's the interesting thing, 1938, well, it's a while ago. There was absolutely no warning whatsoever. None, zero, right? New York Times, I have a facsimile of it, the morning of the storm, cloudy with some rain. Is basically what it said, all right? So we've come a long way since then. It's hard to wrap your mind around. 600 people died in New England from that event and whole forests were wiped out. So none of the storms I'm going to talk about tonight match that storm in magnitude. So remember that, those are the rare big ones. We think there were 3. 1635. If you know some Maine history, that was the storm that ran the Angel Gabriel, the ship, aground in Pemmican Harbor, where I have my boat today. I think I'm going to have to take it out pretty soon. And 1815 was a really big storm that flooded all of Providence, and then 1938. All of these, however bad they were, don't match those. So Hurricane 1954 was an interesting storm because two hurricanes, 2 weeks apart. It seems that storms like to affect Maine in pairs. There were 3 deaths in Maine, 65 and deaths and 1,000 injuries around New England, $10 million in damages, which translates to about $250 million in today's dollars, somewhat more than the double whammy we had in January. $500 million in damages around New England, translating to $12.5 billion today. You can imagine what would happen. There's a lot more infrastructure to harm now than there was in 1954. We had gusts up to 78 miles per hour in Midcoast Maine, 2¼ inches, not that much, but it set the stage for more flooding from the next storm, Edna, which occurred only 2 weeks later. All of Portland was out power, huge damage to the lobster fishing industry here. And 3/4 of our apple crop were destroyed. Very bad timing for the apples. And the closest approach to Rockland, on the other hand, was within an hour of low tide, so there wasn't much coastal flooding. Makes a big difference with a 12-foot tide swing. So there are pictures of ships wash into Falmouth, Maine. And that's a picture of a tree that was toppled. I think that one was, well, it's in Portland somewhere, anyway. This is one that fell on the governor's mansion in Augusta in that storm. That got the attention of the governor. This is a scene of Maine during Hurricane Carol. You really did not want to be out in that. And that's looking southwest from Booth Bay Harbor during the storm. In Boston, it was pretty bad. There's a picture of the 148-year-old steeple. So it lasted a long time until that storm falling during the storm. And then came the second one, Edna. I neglected to tell you the first time I showed you a chart like this. This is the track of the center of the storm. A lot of people see charts like this that are shown up on the weather report on the news, and they falsely interpret this as a signal of danger, that the danger will be confined to that track. And if I live outside that track, I'll be fine. That's very, very far from the truth. So we have to be very careful when we're warning people not to focus their attention on the storm center. But those are the points of the storm center at 0 Greenwich time in September. So the very bottommost point is September 5th and so forth. And the colors are the peak wind inside the storm, according to the scale at the bottom. So for example, when it was off the coast of the Carolinas, it was well over 100 knots, 110 knots. Very strong hurricane. Went into the center of the storm, went into eastern Maine. And 8 people were killed in Maine, about in 2019 dollars, about 240 million, sort of similar to Carol. Peak gusts, again, in the same range. So you can imagine these storms 2 weeks apart, 7.5 inches of rain, but the rivers were already flooding from the previous hurricane. So we had a lot of flooding damage from that. And President Eisenhower is the first president I remember growing up, declared Maine a disaster area. And in this case, the closest approach was a few hours before high tide, so there was more coastal flooding. There's a picture of Southwest Harbor during the storm. I wouldn't have liked to have been riding that out on that houseboat. I don't know about you. Lots of inland flooding. This is a damage to a dam in Limestone, Maine. There used to be a drive-in at Rockport. Some of you might remember. It was actually rebuilt, but during the storm, it was completely destroyed. All right, and then it got rebuilt. And it was inspiration for lots of interesting literature and art. So this is E.B. White, who lived up in North Brooklyn, was very impressed by Edna and wrote this column in the New Yorker. If any of you want that column, you can probably find it, but if you can't, send me an email and I'll send it to you. It's a nice one. Here's a painting by Thomas Hart Benton depicting Edna down in Martha's Vineyard before it came up here to Maine. Okay, so going forward in time, we go forward 9 years. We had a relatively mild Hurricane Ginny, but notice that it didn't actually, the center of the storm didn't cross Maine at all, went into Nova Scotia, but there was a 100-mile-per-hour wind at the Coast Guard station in Rockland, and lots of trees were knocked over. And it wasn't quite as damaging as that, but it was likely a hybrid storm like Sandy. It wasn't a pure hurricane, and the wind field was quite large. So the fact that the center of the storm was well offshore didn't really save us from that. Gerda of 1969, 6 years later, was moving very fast. Notice the big stretch of distance covered between the 9th and 10th of September 1969. It had winds of over 100 knots while it was offshore of New England. And it made landfall as a Category 2 hurricane, probably the strongest hurricane in record to hit the state of Maine. It struck about 2.5 hours before high tide at Eastport. Now, when we go forward in time, there's a big gap. We didn't really have any more New England hurricanes until 1991 with Hurricane Bob. And that gap turns out not to be just a statistical fluke, but something that we collectively caused. It's a very, very interesting story. I can get going on these stories and we'll be here all night, so I'm not going to do that. But I will tell you this. This is a record of the frequency of major hurricanes in the Atlantic Ocean. A major hurricane is Category 3, 4, and 5. Okay. So the strong hurricanes from 1851 to sometime in the 2000s. And okay, there are ups and downs. There's a lot of variability from year to year. That green line is just a smooth version of the red lines. And you notice this pronounced dip in the 70s and 80s. And then it comes back, comes roaring back. That happened not just in the Atlantic, but mostly in the Atlantic. And we now know that we caused that. Anybody want to guess how we did that? Not purposely, of course. What got really bad in the 70s and then got better?
Air pollution?
Yeah. Yeah, it was particularly the sulfates. And it's a long, complicated meteorological detective story. But it was Northern European sulfur emissions were carried out in the summer circulation down over the Mediterranean and Africa, where they shut down the African monsoons. They had terrible droughts in that period of time. Because of that, it got very windy at the surface, and a lot of sand and mineral dust was lifted off the Sahara and blown out in the trade winds, which blow from east to west over the Atlantic. And that dust combined with the sulfates themselves blocked sunlight in that region, which is a breeding ground for hurricanes, and shut it down. Okay, so we went through 20 or 25 years of almost nothing. There were a few storms in there, but very few. And during that time, there was huge construction of the development of the US coastline, particularly in the South, not so much up here. And we were setting ourselves up for disaster. The Clean Air Acts kicked in the 1980s and 90s, cleaned it up. Very good thing they did, but there was a black lining on that silver cloud that brought the hurricanes back. So we did that. We did that. So we have to go fast forward now. We skip over the hurricane drought period. Oh, by the way, that blue line is the scaled and inverted European sulfur emissions. So you can see the relationship between the two. I've just turned it upside down. The emissions went up, of course, then. I just turned that curve upside down so you could do a visual comparison. Here's the next hurricane, Bob. How many people remember or experience Bob? Oh, fair number of you. Yeah. Yes, my wife and I had been married a year. We saw all the people fleeing the Cape right after the storm. We said, let's go. They're going to have low rates in the hotels. There's no power. We checked into a dark hotel. And as I was writing in the register, the lights came back on. The proprietor said, now you have to pay full price. They're not as nice down in southern New England as we are here. Okay, so here's the track of Bob. And once again, you see this characteristic of it moving very fast. Look at how much territory it covered between the 19th and 20th of August. It was really moving. It wasn't as strong as some of the other storms we've had. It went right up along the coast of Maine. I wasn't here for that. It made landfall near Rockland. It was one of the costliest hurricanes in New England, about 1.5 billion $1991, or $2.75 billion. 3 deaths in Portland, gusts to 70 in Portland, 92 in Wiscasset. That would do a lot of damage there today. 8.25 inches of rain at Portland, 170,000 people without power. That happens a lot in Maine, though. I don't know if that's particularly extraordinary. There is an unconfirmed tornado, which are often associated with hurricanes, at St. Albans, a 2 to 3 foot storm surge, and river flooding washed out 5 bridges and roads in southwestern Maine. But it occurred, thankfully, at about the time of low tide, so there wasn't all that much coastal flooding up here. And then finally, I couldn't resist putting this up. This would have been a little bit more relevant last year. This is Hurricane Lee from 2023, and the center didn't pass over Maine, but we still had a lot of power outages and trees down in Maine from that storm. And there was an emergency declaration for the state as a result. Okay, so now let me turn from the history of hurricanes in Maine to a discussion of how we deal or how we assess how much we're at risk from hurricanes here, and should we be worried, and what should we do about it? And I'm not going to talk too much about the last 2 points because it isn't really my field, but tell you what we're trying to do to set things up for people who do worry about such things. I want to talk to you a little bit about the general nature of the problem of natural hazard risk. And it's actually an anthropological point I want to make to you all. And it's pretty obvious, you know, societies are well adapted to frequent events, right? 30-mile-per-hour wind happens all the time in Camden, and it's not going to do any damage because we experience it all the time. We build for it, right? At the other end of the spectrum, we're poorly adapted to rare events, particularly ones we've never experienced, right? But are at least physically possible. And it turns out that the dividing line, this is empirical, it's just from studying history, is about once in 100 years. If it's less frequent than that, it's probably going to clobber us. If it's more frequent than that, not so much. So if we put that on a little cartoon, let me just say first that we need, do I have that cartoon? No, I left it out. All right, it doesn't really matter. It just expresses in a picture what take a lot longer to say in words. If you want to know what the 1 in 100-year event is, right, you really need about 1,000 years of data. And this is the problem with insurance. We don't have 1,000 years of data. We don't even have 100 years of data. So typically we don't know what the 100-year event is, right? It's when some kind of change, like climate change, takes storms that may have been once in 150 years events, and they become 1 in 50-year events much faster than society can adapt to them. That's when we have a problem, all right? The 1,000-year events don't matter because they're so rare that, you know, if they become 800-year events, it's still very, very rare. And as I said before, the 20-year events don't matter either because they don't really cause much damage. It's right in that middle part that we have to worry about that. We don't have 1,000 years of meteorological observation, so we need to be a little bit more cagey about how we do this. And so what we have done at MIT is to get away from purely historical statistics and use physics to estimate risk. So Here's what I mean by that. If you go out to buy an insurance policy, as many of you have at one point or another, say a house insurance policy, and they charge you a certain premium for it, what are they basing that on? Well, they're basing that on an assessment of risk that's in turn based strictly on historical records. So the so-called catastrophe modeling companies that try to inform the insurance companies about this risk hire armies of statisticians to pore through this very slim historical record of storms and try to tease out of that some assessment for how likely these hazards are going to be. Well, they're trying to pull a rabbit out of a hat, okay? And they're doing the best they can. They're talented people, but there just isn't enough, particularly in a place like Maine. I showed you practically all the hurricanes we've had in the last 70 years or so. Right now, I didn't have to spend all night doing that. For Florida, it'd be a different matter. There just isn't enough history. So there are other ways of knowing about the world, and one is by understanding the laws of physics that control things like storms. And fortunately, in the case of hurricanes, we do understand them pretty well. I thought about spending some time talking about those laws tonight, but my mother told me never to talk about mathematics after dinner, so I left it out. You might be grateful, but if you're interested in that, I can point you to something. So they're very, very interesting storms. And so we're going to do something a little special, a little bit different, and this is kind of the future. A lot of companies and other entities are beginning to do this now. And it is one of the reasons, unfortunately, well, fortunately in the long run, unfortunately short run, that so many insurance companies are going out of business, because we've come to understand that the risk now has already increased appreciably from 50 years ago, where all those statistics were collected. So the fact that we're basing our risk on historical statistics, even if we had 1,000 years of data, they'd be largely irrelevant now. I'm not talking about the future, I'm talking about what's already happened, okay? So you'll see that as I go along here. So just very briefly, what we do, the problem with the global climate models is, or even global analyses, even global weather forecasting models, is that they don't have enough spatial resolution. Computational nodes are too far apart to capture the strong inner core of hurricanes. And they don't. They produce some messy kind of thing that looks a little bit like a hurricane, but it's really no good. And so what we do is we embed within this large-scale feature, large-scale fields, a very fast but highly resolved coupled ocean atmosphere model of a hurricane that we originally developed and is still being used to help forecasters forecast how strong hurricanes will get. Okay, they were using them in Helene, for example. So what we're able to do is to use the statistics from these large-scale models to drive this much more refined hurricane model. And then by doing that, we can, for a given climate, generate hundreds of thousands of synthetic hurricanes, where you do have enough statistics at least to get it right. Well, fine, I've left out all the details for you because it's after dinner, right? And but how do we know it works? You only know it works if you can compare them to historical events. So history is valuable for that reason. At least you can compare them where we do have reasonable histories, like the East Coast of the US. So this is just a chart showing 1,000 of a much, much larger set of hurricane tracks around the world. It's obviously you want to do much more objective quantitative comparisons, but if it doesn't pass an eyeball test, it's not going to work. Sorry, I pushed a few wrong buttons here. Let me see if I can go back. There we are. By the way, there are no storms near the equator. You have to be able to take the Earth's rotation, its axis points from the South Pole to the North Pole, and project it onto what you're locally calling up, and get an answer that's not zero. But at the equator, it's zero. So if you're sailing around the world and you don't like hurricanes, stick to the equator, though you may have other problems there. Well, this is what you can do. This is a chart showing the what's called the return period of winds from hurricanes along coastal New England. So what a return period is, return period of 100 years literally means that every year there's a 1% probability of having that wind speed or larger. So when you hear a 100-year event, don't think every 100 years you're going to have that. That's not it. It's the probability each year is 1 in 100, okay, or 1%. So the higher return periods are associated with much rarer events. And so that wind speed curve goes up. The green dots are what you get from analyzing all the historical storms that have crossed the coast of New England. The blue dots are what you get from applying physics to the problem. And the red curve is just a curve fit. You can ignore that. But the point is, we can go out to much longer return periods than you can with historical data. We can get the easily, actually, we haven't done it here, but you can easily get the 1,000-year event. You certainly want to get out to a few hundred years for an appropriate assessment of the risk. You can refine this, and I did this for the purposes of this talk and one other I gave, is to look at filter storms so that you consider a large set of storms, all of which cross the coast of Maine. That is, you just throw the other ones away, essentially. So here's a set of the top 50 in terms of their wind speed when they cross the coastline of Maine, the top 50 out of a set of 1,800 tropical cyclones, which represents many thousands of years of tropical cyclones in the coast of Maine. And these are the tracks, and their color. The colors show that are proportional to the peak wind. Red is category 5 of the storm. So you notice that almost all of them that are really strong, these are the strong ones. Now, these are stronger than any that have been observed, just because, again, we can look at much rarer events this way. All the strong ones come from between the south-southwest and the south-southeast. They're not coming at us, for example, from due east. And there's a very good physical reason for that. All hurricanes that affect Maine, all of them are dying. The water is not nearly warm enough, not even to swim in, much less sustain a hurricane. They're all dying, and the strong ones are moving really fast. So they haven't had time to spin down after leaving the north wall of the Gulf Stream. So all the strong ones are moving in a straight line pretty much fast. They just haven't had time to spin down since they've been in the tropics. That's all. It's very simple. If I showed you the weak ones, they'd be all over the map. You have some coming from the east and so forth. So what we can do with that is make charts like this. This is just, again, storms affecting the Maine coast. On the vertical axis is annual exceedance frequency as a function of wind speed in knots, is our quaint nautical unit of velocity. So, for example, oops, I did that again, didn't mean to leave that chart. It shows that the annual, gosh, what a, I'm not supposed to be practicing the piano up here. So the probability of getting winds of more than 40 knots, the coast of Maine is like 0.13. So every 7 or 8 years, you might see something like that. It's a very weak storm, all right? Whereas if you get down to 80 knots or so following the red line, it's once more like once in 100 years. The blue dots are what you deduce from history. And there are very, very few storms in history, as we've just seen, crossing the coast of Maine. The blue is what we call an estimate of the sampling error from history. And basically what it means is the red line falls within that blue envelope, or the blue dots fall within the blue envelope. You can't reject the hypothesis that the synthetic tracks are like the historical tracks, the actual tracks. Okay. This is what a 500-year event would look like on the coast of Maine in the current climate. This is just a randomly selected event. And you can see it's moving very fast. This happens to be in September. And we downscaled a climate analysis that spanned from 1979, I think, into the 2000s. This happens to be 1982. And this is something that could happen, but very, very, very rarely. If it did happen, we'd be in trouble. We don't tend to pay much attention to events that are this rare, but it makes landfall in Maine as a good Category 3 hurricane or so. And it would be devastating, particularly for Penobscot Bay, if it happened. You don't see that in history because we would need 5,000 years of history to make that, to get a reasonable chance of having a storm like that. Just as focusing in on the same synthetic hurricane, showing in contours and colors the peak wind experienced at every point on that map in the course of the storm. And you can see how rapidly the winds fall off. The center of the storm is passing from south to north along that black line. The strong winds are always off to the right of the track in the northern hemisphere, because in some sense, the translation of the storm is adding to the winds that are going counterclockwise around the center on the right side. So you can see by looking at the color scale that we're getting 80 and 90 knot winds along the coast, but of course tapering off pretty quickly. Inland, although still 55 knots, up in northern Maine. When we look at chart, when we look at all this data, we can make simplified charts like this, which shows in colors the measure of a quantity called power dissipation. It's a little technical term. It's a measure of how powerful the storms are when they cross the coast. And I've divided the coastline into 4 segments. The blue is not much power. The red is a lot of power. Just to illustrate, I haven't put numbers on this, but just to illustrate that hurricane risk in Maine decidedly increases as you go east, which may be a little counterintuitive to you. It's just that storms down in southern Maine almost always have to pass over a lot of land before they get there. Whereas over by Eastport, they don't. They can stay over water where there's less friction and keep going. This is the track of a storm whose winds are quite weak. What was a 500-year rainstorm for Maine, for Midcoast Maine. And if you look at that, it's moving pretty quickly until it gets to Maine, and then it stalls. And that's a recipe. That's what happened in Helene a few days ago. And this is just contours of the total rainfall in inches from that storm. So over the whole course of the storm, you had over 8 inches of rain in places, which is quite commensurate with the worst storms we've seen in history. 8 inches in Maine is a lot. It will cause a lot of rivers to flood. 8 inches in Mississippi is every other day, sometimes in the summer. But so finally, I want to get to the point of how will climate change affect Maine hurricanes. And so what we do there is apply the technique not to global climate analyses, which is what I've been showing you, but to global climate models run forward. Now, the problem with running forward is the old adage that's traceable back to Niels Bohr, the physicist, that forecasting is very difficult, particularly when it involves the future, right? And whenever you go out in the future, you get lots of uncertainty. And global models don't even agree on things very well, like the global mean temperature. But if you ask them, to produce reasonable sets of winds and temperatures in a region, like coastal Maine, they're all over the place, all right? Nevertheless, we do this because we like to at least bracket, if we can, the possibility. So in this case, we use 7 of the most recent generation of global climate models running only 1,600 tracks, but that's well over several thousand years worth in the climate of Maine. From each model, for each of 2 time periods, the late 20th century to 2010, one case, and the end of the century, 2061 to 2100, under a relatively moderate emissions projection of carbon dioxide emissions. And they're filtered to pass within 125 kilometers of my hometown, New Harvard, which includes Camden, where we're not that far. And this is sort of the end result of this, so you can see the effects of climate change. So a lot of packed into this chart. Again, this is the annual exceedance frequency. So 0.01 means once in 100 years, if you will. And once in 100 years, you will get, I think I put some dots on this chart. Well, a 50 knot wind, if you look at the bottom axis here, would occur about every 70 years in the climate of the late 20th century. So the blue pertains to the period 1971 to 2010. The red applies to the period 2061 to 2100 under this moderate emission scenario. The curve is the mean from these 7 climate models, the solid curves, and the shading represents a measure of the scatter among those 7 models. You can see it's pretty large, right? Depends on which climate model you want to run. They're all calibrated to get kind of the right answer for frequency in 20th century, which is why they all convert. There's not much shading at 40 knots on the historical side. But when you go out to the future, the uncertainty gets bigger. But you can see the blue and the red are pretty well separated. So that means there's a strong consensus of climate models that wind risk from hurricanes in Maine will go up over the century. So, for example, 50 knots would occur, according to this analysis, somewhere on the coast of Maine. Well, actually, it's within 125 kilometers of New Harbor. And this is actually, sorry, I should look at my notes. This is estimate wind risk not for a region, but for a particular point. And I did this for a study I was doing with Jim Bennett, rest in peace, earlier in the year. Wanting to understand what kind of winds were going to drive surges into Camden Harbor. That's why we picked this point. So 50 knots from a hurricane every 73 years. Now you're going to get 50 knots from a winter storm much more frequently than that. But by the end of the century, more like once every 25 years. So kind of almost a tripling of the frequency of that magnitude of wind. We go further down the curve, 64 knots, which is the dividing line between a tropical storm and a hurricane, every 300 years, almost never, in other words, in the climate of recent past, going to every 84 years, once every few generations in the future. So this is the sort of thing that we're doing and trying to help inform people like, or outfits like insurance companies and towns and cities to help them prepare for the future. So here is the track of, again, a 500-year windstorm, but one for the end of the century rather than the last 30 or 40 years. And this comes roaring out of the south. It's a Cat 5 hurricane with winds of 140 knots when it's offshore Florida, but it's moving very quickly, and I think it makes landfall here as a Category 4 hurricane. Very rare event. You won't see this, all right? It's too rare. When you generate 10,000 hurricanes, you will see things like this. It means it's possible. It's just very, very unlikely. This is just a zoom in on that. You wouldn't want to be around here when this happens, if this ever happens. So 120 knots just offshore. And this is the same thing for rain. So this is the blue curve again is for the recent past. The red is for the end of the century. The curves are the mean of these 7 models, and the shading shows the scatter. So 5 inches of, this is again, actually this is for a point in Union, Maine, which is arbitrarily picked that as an inland point. 5 inches of rain every 250 years in round numbers for the recent climate. So almost never, but every 20 years in the future climate. That's a huge increase. This is the point I want to really emphasize before I wrap up. Hurricanes are about water. They're really not about wind. I mean, yes, if you're offshore, you have to worry about the wind. It's really about water. And when it comes to climate change, it's really about water. This is very, very simple physics. You make the air warmer, it can hold more water. But the storms are also more intense. Both of those factors contribute to heavier rain. So what I'm really worried about in places like New England is the potential for not just coastal flooding, but inland flooding from events like this. And you can see how well separated those two families of curves are, the red from the blue. It's a big signal. And we get 9 inches, really never in the previous climate, 10,000 or 5,000 years, 4,000 years, essentially never. But, 150 years in the future is not never, it's still rare, but something that engineers anyway would want to try to design for in many cases. And there's the track of the 5-year rainstorm. Again, not that impressive in terms of wind speed. It occurs in September of 2096, this one. And again, I mean, these dates are random. It's not like we're going to have that hurricane in 2096, but we could have a hurricane like that. But this is an extremely rare event, and it would produce well over 14 inches of rain in Maine. So let me wrap up, because it comes to my favorite part of these talks, which is your questions, okay? Maine is mostly protected from hurricanes by the fact there's a lot of cold water. Even though the Gulf of Maine is now 5 degrees or so warmer than it was 40 years ago, it's still very cold, still too cold to sustain a hurricane by far. So you don't have hurricanes forming off the coast of Maine, even in an extreme warming scenario. There were, if you turn the clock back 50 million years, when there were crocodiles in Canada, yes, but not in the recent past. And so the cold water really extends down to the north wall of the Gulf Stream, and we're also protected to some extent by the Cape and the Islands. But we have experienced in the past, I've shown you several low category hurricanes, tropical storms, which have caused damage and taken lives. The risk increases as you go east. It's worse in Eastport than in Camden, and Camden is worse than Portland or places south in terms of hurricane risk, even though you're also going a little bit north. It's just a question of hurricanes staying out over the water. They're spinning down, but they're not spinning down as fast as they would if they were over land. If we don't do anything about the greenhouse gases, the projections suggest a modest increase in the frequency and severity of hurricanes in Maine by the end of the century. Large projected increases in hurricane rainfall are the big concern for people in my business. It's the wind, it's something to worry about, but the rain is really the big thing. And we're working on the problem of hybrid storms like Sandy, which may not be so well simulated with the techniques I've been talking about. So that's sort of a once over lightly about hurricane risk in Maine. I hope I persuaded you that no, you shouldn't lose sleep over things. But if you're in the business of planning, as I know people in this room are for the future, it helps to know a little bit about what to plan for. Rising sea level, which I haven't talked about, and increase in the incidence of these storms. One other thing I haven't said to you is winter storms, right? Believe it or not, although there are a lot more winter storms, we know less about how they will change in the future at this point in history than tropical storms. If I get invited back in 10 years, I might be able to tell you about the winter storms. Okay, thank you very much. Are you going to select the question?
No,
I will.
I'll let you in.
Okay, yes.
I was a young teenager here with my family at our place on the lake, summer time only, when Carol came through.
Oh.
My vivid memory of that is the harbor, apparently people didn't get much warning. They didn't bring boats in, and the wind just swept that harbor. There were far fewer then and now, but it took 8 or 10 large yachts and sailboats and piled them on the rocks outside the yacht club. And I remember walking down that little loop road and just looking at masts and hulks and boats, enormously damaged in terms of the value, I suspect, and the family concerned for that. But that was an image of what that storm was capable of if you didn't prepare and take precautions ahead of it.
Right. And it also is a great illustration of how much progress we've made in forecasting hurricanes. That it's unlikely today, almost impossible, that you get no warning for a storm like that. But the fact is that the storms that really get us are moving very fast. So it is conceivable you wouldn't have much more than a day under some conditions. But you probably know there was a chance of it anyway, a few days out, but you wouldn't really know until a day for the really big ones. But yeah, made a lot of progress. Yes.
Comment on Edna. In Bath, we got 11 inches by
Oh, really?
measurement.
Yeah.
My tin can.
That's a lot. I mean, this is another problem is Maine doesn't have a lot of official rain gauge stations. So information like what you just told me is very valuable for that. Was there flooding?
Oh, yes.
Yeah.
We had in a garden patch that hadn't seen water for a very long period of time, beneath the amount of water. The major stream backfilled some areas to the west of us that we hadn't anticipated. And it was a regular torrent that came down through our garden area. There should have been a hint for us because there had been a tannery across High Street that had long since been out of service, but apparently in colonial times there was a stream that flowed through there, but it had been basically sequestered by development along what was the former stream path, and it was sort of filled in over time.
That's something that we have to worry about. Yeah. I'm embarrassed to say this, but this proved to be the case at MIT where I worked, because they had lost track of where some of the underground streams were and some of the underground conduits that were man-made. The city of Cambridge had them for Cambridge, but not for MIT. So Cambridge had better records of the engineering structure than MIT had. Pretty embarrassing. Yes.
By the way, Kerry, I'm Joe.
Oh, Joe, thank you for coming. I was hoping you'd be here. Yeah.
So the tracks, they're fascinating. And one is that it looked like almost all of them were over water trajectories right into Maine. But the formation areas, they're not Cape Verdes. Yeah. They're closer in, and also in the higher subtropics. Right. Yeah. So in other words, this isn't a storm that would be, 13 days coming across the ocean or 12 days coming across the ocean. This would be formation, and then here we go.
Yeah. Yeah, I think I was showing you very selectively the cream of the crop, if you will. And in some sense, to get a really strong one here, it sort of has to reach its peak intensity at the north wall of the Gulf Stream. If it peaks before that, it will already be winding down even when it gets there, because they sort of have these lifetimes. And yeah, glad to meet you across the room. Yes.
I have a question that's a little bit broader than just hurricanes, but sort of these big rain events in general. And we've seen some really big rain events in Maine as well. Like Vermont's had a couple of huge ones in the last year or so, a lot of flooding. I wonder if you can talk a little bit more about what we know and what we don't know about the frequency of these much bigger and more dangerous rain events in New England.
Yeah. Well, I can say something very broad about that, but not very particular, because it really depends. I like to say all climate change is local, like Tip O'Neill used to say about politics, right? Really what matters is the region. But what we understand better is the global or larger scale problem. And that is that as you warm the climate, two things happen. The global amount of rainfall, literally the rainfall averaged over a year around the globe, it's very constrained not to rise much. It rises a little bit as you warm the system. Very interesting physics behind that. But we have this constraint. You can't really mess with the annual global rainfall. However, the amount of water vapor going up into a cloud, which is approximately equal to the amount of water coming out of the cloud, goes up very quickly with temperature. So how do you make that work? You're going to have a lot stronger, heavier rain, but you can't change the global total. So the rain becomes, in some sense, less frequent. So it's a very solid prediction of physics that rain becomes either less frequent, or it certainly becomes more intense or less frequent, or in some extent, a mixture. Places that are already kind of wet, like the Mississippi, lower in the Mississippi, get wetter, and places that already are dry get drier. And we see that both happening in models. And so, but from the point of view of flooding, we can get now much more intense rains than we used to. I'll give you a concrete example. Hurricane Harvey that flooded Houston. As it happened, right after that storm, 3 independent teams, we literally didn't know about each other at the time. We knew who we were. We didn't know we were working on the same problem. My group was one of the teams, tried to assess how the probability of that amount of rain in Harris County, for instance, had changed. And we all came to the conclusion that the probability of that amount of rain in Harris County had increased from 1970 to 2017 by a factor between 3 and 6. Okay, now, so all of the design criteria for the infrastructure of Houston was based on statistics centered around 1970. They were really, really badly out of date, but that's what they're getting from the CAT modeling industry, which is stuck with historical statistics, is why we're trying to move into physics and away from pure history. Yeah. Yes.
Oh,
Yep.
You've mentioned that you're using physics to estimate hurricane risk. Is there lab gear involved? Is this a Draper lab?
No, there's no laboratory. It's all done on computers, actually.
Okay, all right.
Yeah.
I didn't know. I couldn't quite tell. 'Cause
Sorry.
I wondered about scale factor, because like
Yeah.
right now, we're preparing to create wind turbines, offshore wind turbines.
Yeah.
And one of the things is the question was about scale factor. And as a physicist, can you assess from looking at some of the different models there are about whether scale factor is anything we need to be heavily considering, or is that something that's easy to understand and not worry about?
Well, it's interesting because when Cape Wind was a thing, was it 10 years ago, something like that, they actually hired my group to try to understand their exposure to specifically hurricane risk. And it's pretty substantial out there. And they tried to take that into account, but I don't know what actually happened because that company went out of business. But yes, we can do the hurricane part of that pretty well, but not the winter storm, not yet. And that's a big factor up here. There was a question in the back too. Yeah.
Yeah, thank you. I'm Dr. Emanuel. I work at OCP. The question would be, what are the blind spots that concern you where we could be thinking about directing funding to help Joe and his colleagues, to help the academic community as you look towards the future? Where are things that we're not addressing now that we could be investing in to better understand longer term, low frequency, high impact incidents? Also, by the way, I ran the MEPA program in Massachusetts and was closely involved in reviewing Cape Wind and Jim Gordon, and I can tell you all about later on.
Oh, good. You want to go have a drink after that? There are quite a few. I mean, one of the things that I saw right away, and I might be misled about this sort of paucity of surge of tide gauges on the coast of Maine. I thought it was pretty, compared to other regions. That seems like an easy thing to fix. So I might be underestimating it, but that's not a research problem. But I don't know. Joe, do you feel that way about the tide gauge distribution?
There are commands to move us to not have the sort of the hard high level gauge, but actually there are less expensive gauges that still have some quality that are in discussion or towns are putting.
Right.
But yeah, I think it's too far a distance.
But from the research perspective, I think thing I would try to pay attention to are the hybrid storms. Trying to get a handle on that these are not well resolved by climate models. A bit better than hurricanes, but still not well resolved. And we don't know how to downscale them very well, except by the brute force technique of putting finer meshes in certain regions. And we've done a little bit of that. But I think that's true. But the main thing is that I have to emphasize again, it's the water. And we have this situation, you know, well, in the United States, where almost all water damage, unless it's from a broken pipe in your house, is insured by the federal government. And the private insurers who put a lot of resources into risk assessment are all concerned about wind and other things. And so the water being the worst thing gets neglected in some ways. All right, and I feel it's neglected. And this last storm, I mean, all the focus, people were all focused on where Helene was going to make landfall. And of course, it did some damage down there, but nothing compared to what happened inland, where there was no attention until it was too late. Now, I mean, forecasters did pay attention to it, but the message didn't really. It's an art of social science, how you communicate a risk like that to people. And I don't think it's being done very well. So that's another, we could go on. Yes.
About 20 years ago, there was a magazine called World Watch and an institute behind it, which was founded by Lester Brown, who watched the crops, the agricultural weather, the world for grain companies. And the World Watch had an annual State of the World environmental report. And it disappeared about 20 years ago. And one thing that was predicted at that time was that the insurers of the insurance companies were going to start to get anxious about climate change. And that was going to really get people's attention. Well, they somehow fended it off, but you're beginning to talk about it again.
It's the sort of 6,000-pound gorilla here. It's worth a talk on itself. It's almost, I've sat in on companies, insurance companies, board meetings for quite a while. And I used to think it was the most boring enterprise you could think of, but it's just the opposite. It's all about human nature, but it's very complicated. But the bottom line is that in the United States, not through any Machiavellian plot by anyone, but just how it's worked out, we're massively subsidizing people to live in risky places and bailing them out. And the people who are living in less risky places are paying for it, paying the bills. And it's kind of crazy. We're just doing exactly the wrong thing. Everybody is beginning to realize that. When I first started to talk to insurance companies about climate change, they said, well, we're writing one-year contracts. So what do we care about 50 years? I said, yeah, but the one-year contracts are based upon historical statistics that ceased to be relevant to your enterprise about 30 years ago. That got their attention. And they now, I think, pretty much realize that. Excuse me.
There's some questions on Zoom.
Okay, fire away.
So someone is asking, did you see Maine's 3 landfalls in 2023 per the NHC, most landfalls of any state last year? Do you think that could happen again in the next decade? Thank you.
So I'm going to take the question to be a little bit broader. I'll broaden it out. And one of the things we're very concerned about is clustering of large events. It's not like there's a natural tendency for them to be clustered, but you know, I used to like to do this for my students, you pour a lot of table salt in your hand, you throw it up, you let it land on a black table, try it yourself at home, right? And yeah, you can do this, it's not dangerous. And you can pick out all kinds of patterns and triangles and hexagons and clusters. And they are there, but they're random, they're accidental. If it's nice ordered lattice, that's not random at all. And so that clustering of events is what typically sinks insurance companies. Yeah, they designed for this storm, they got it, bam, right? They made it through, and the next year, something similar happened just by random chance, and they're done, right? So we're getting better at that. And this sort of the question is how much of this three in a row is sort of accidental and how much of it is not. It depends on the time scale, but yeah. Oh, yes.
Hi, Dr. Manuel. I'm a local school teacher here, and
Mhm.
you just spoke my language with shapes and kitchen tables. I recently started working with a naturalist and outdoor ed coach to get my kids outside and experimenting and exploring in our natural habitat. And I'm just wondering, because I've learned from this coach that you can teach climate science at a young age, and it doesn't have to be MIT level physics.
Right, sure.
And so I'm just wondering if there are any little experiments, collecting rainwater or models that we can build or create that I can just engage little kids in.
Yeah.
To get them thinking like this from a young age.
Oh, there are lots.
Yeah.
Somebody
Great.
should write a book of these, because it's a really great idea to get them thinking. One of the things that I did with my students, even though they're graduate students, they could have been third grade students for this experiment, is to, most people have cars parked in their driveway or a truck, it doesn't matter, as long as you have a metal surface that is exposed to the sky. And I said, go out on a cloudy night, measure the temperature of the air, and if it's not raining, but it's cloudy, and measure the temperature, put your hand on the hood and say, is it really warm or cold? Assuming the car hasn't been running recently, right? Go out on a clear night and it's way colder than that, okay? You find that the hood of the car can get way, way down below the temperature of the air. And it teaches them about radiation. It's radiating to space, it's losing heat to space. When they're clouds are greenhouse agents, they're radiating back and keeping the hood warm. It's really simple. And I'm sure there are variations on the theme, but yeah.
Thank you, I appreciate it. Another question on Zoom.
Yep.
What would you say to someone who would perceive Maine as a climate haven?
Good luck with that. You know, I'm tempted to say the coast is riskier, but it's not as risky as the coast of North Carolina, for example. I'm tempted to say that inland is safer, but you know what happened in North Carolina could happen here. Now, they'll never get that amount of rain in Maine, okay? But this goes back to one of the first slides I showed. We're used to a certain level of rainfall or a certain frequency of high rain events, and the infrastructure reflects that. You go up to a new level, whether it's in North Carolina and Maine, things start to fail. And so we have to be worried about that. One of the tragedies, and I think unfortunately you're going to see death tolls in the hundreds of people from the storm, Helene, is that it's very, you know, if you're living next to a river, yeah, you tell people, look, you better get out. Most of them will. If you're living on a hillside and there, you know, you may not get a warning that something's going to happen, like you were describing, a little gully that you didn't even worry about. It's going to fill with water and wash your house down. You know, that's happening a lot, or did happen a lot in Helene. So you can run, but you can't hide. And that's unfortunately the way it goes. But there are less risky places for sure. We shouldn't be subsidizing people to move to the riskier ones. Anyway, yes.
I'm going to get these on, but you know, there's a lot of discussion about the shifting major North Atlantic currents, the Labrador and Gulf. And when you look at those, are there assumptions about those? Just work into those climate models that you have, or is there potential that that's going to be wackier even than, and that there'll be a big change that?
Yeah, that's a good question. I mean, the currents you're talking about in the ocean transport a large amount of heat, about a third of what the atmosphere transports from hot regions of the tropics toward the poles. And you mess with that, you really change the climate. The physics are in the models, the climate models, they know about that. But if you talk to professional oceanographers, which I do all the time, there's not a lot of faith that we're capturing those physics well. And what we are a little bit, what keeps us awake at night to some extent is if you look at sort of models at the geological record, particularly ice cores and deep sea sediment cores, you see, particularly during cold periods, ice ages, very, very rapid transitions, what apparently very rapid transitions of the climate, which you might call tipping points, some people do, where things just jump to a different state. And climate models don't tend to do that. And people who are trying to reproduce these by running climate models in the past aren't seeing very much of that. So we know it has happened. And that's about all we know. We're not in a position yet to be able to say there's a low or high probability that will happen going forward. But there are events that we worry about, like the sudden collapse of parts of the Antarctic or Greenland ice sheets that would raise sea level quickly. I think we're making a lot of progress, but we're not there. And we're not, it's these low probability, it's things you don't know that are keeping us awake at night. So yeah, it's a good question though. Yeah.
I'm trying to puzzle through the total global rainfall is a constant, and I'm thinking back historically to during an ice age versus when much of the globe was more tropical. And you're saying rainfall was constant during those periods. And I'm thinking, well, practically a puddle on my driveway in July disappears much more quickly than a puddle in January.
Yes.
And if total global temperature goes up, evaporation seems like it's going to follow suit and quicken.
Yeah.
Once it goes up, it's going to come down someplace and count as rainfall.
Right.
So that's where I'm stuck.
Okay, so to speak a bit more precisely, as you warm the climate, the global rainfall does go up, but slowly. Okay, and so evaporation rates from the ocean go up slowly and so forth. The physics behind that is that when water condenses in the atmosphere, it releases heat, same quantity of heat that was used to evaporate it. So you're heating the atmosphere. The atmosphere has to get rid of that heat to be in balance. It does so by radiating space. So there's a direct relationship between how much the Earth is radiating to space and how much precipitation is falling around the planet. And that amount of radiation is fairly sophisticated. Physics doesn't change very much as you put carbon dioxide in the atmosphere. Temperature does go up, the temperature goes up, but the evaporation rate only goes up slowly, whereas the amount of water going up into a cloud or evaporating from your puddle goes up quickly. So it sounds like a contradiction. The way nature figures it out is to make it rain hard and evaporate hard in a few places and rain not very much in a lot of other places.
I think we have to wrap up so we have time to get out, but thank you so much.